On August 4th, 2026, 2 days ago, NASA's Jet Propulsion Laboratory completed what engineers had been calling the Big Bang. Not a metaphor. The literal name given to a simultaneous irreversible power swap procedure carried out on a spacecraft traveling 3 billion miles from Earth, in temperatures approaching negative 459 degrees Fahrenheit, through a region of space no other operational instrument has ever reached. The engineers waited nearly 2 full days for the confirmation signal to travel home at the speed of light, and when it arrived, it told them something that almost nobody outside the Voyager mission team had expected to hear in August of 2026. Voyager 2 survived. 3 instruments preserved. 1 more year of science bought from the edge of everything, and one of those 3 instruments is the Plasma Wave Subsystem, the instrument that, for the last several years, has been picking up something from outside our solar system that scientists still cannot fully explain. That is where this story begins. Not with the Big Bang procedure itself, though that story alone is extraordinary enough to command its own dedicated examination, but with what the instruments that procedure just saved are actually hearing in interstellar space, what they have been measuring since Voyager 2 crossed the heliopause in November 2018 and became only the second human-made object in history to enter the space between stars, and why the specific frequency being detected by the Plasma Wave Subsystem in the interstellar medium carries implications that scientists are still actively working to fully interpret. Let's build the complete picture. Because, without the full context of what these instruments are, where they are operating, and what the physical environment of interstellar space actually is, the significance of what the Plasma Wave Subsystem is detecting will not land with the weight it deserves. Voyager 2 was launched on August 20th, 1977, 19 days before its twin Voyager 1. The counterintuitive launch order was deliberate. Voyager 1 was aimed on a faster trajectory designed to reach Jupiter and Saturn quickly, including a gravity assist flyby of Saturn's moon Titan. Voyager 2 was launched on a more leisurely trajectory, a grand tour route that would use gravitational assists to reach Jupiter, Saturn, Uranus, and Neptune in sequence, the only spacecraft ever to visit all 4 outer planets. By the time both probes completed their planetary surveys, they had been redirected by the solar system's gravity to head outward on separate trajectories into the interstellar void, each carrying a golden record encoded with the sounds and images of a civilization hoping something might one day find it. 49 years later, both spacecraft are still transmitting. As of August 2026, Voyager 1 is more than 15.8 billion miles from Earth, and Voyager 2 is over 3 billion miles from Earth. Voyager 1 is the most distant human-made object ever built. No spacecraft has ever been farther from the planet that created them. What separates where they are now from anywhere any spacecraft has been before is the heliosphere. Understanding the heliosphere is the key to understanding what the Plasma Wave Subsystem is actually detecting. The heliosphere is a vast bubble created by the solar wind, the constant stream of charged particles, electrons, protons, and heavier ions, that the sun continuously exhales in all directions. That wind expands outward from the sun at hundreds of kilometers per second until it meets the interstellar medium, the thin but real material filling the space between star systems. At the boundary where the solar wind slows, compresses, and eventually loses the battle against the inward pressure of interstellar material, the heliosphere ends. That boundary is called the heliopause. Inside the heliosphere, even in the outer solar system billions of miles from the sun, the environment is dominated by solar wind particles and the magnetic field they carry. Outside the heliopause, the environment is completely different. Interstellar space is filled with plasma, ionized gas that was ejected by the deaths of massive stars millions and billions of years ago. It carries its own magnetic field, oriented differently from the sun's. It contains cosmic ray particles that the heliosphere normally deflects before they can reach the inner solar system and the Earth. And it has its own acoustic properties, its own frequencies of electromagnetic oscillation, its own plasma density that determines what waves can and cannot propagate through it. Voyager 1. Whereas 1 crossed the heliopause in August 2012 and entered interstellar space, Voyager 2 followed in November 2018. These crossings were not guesses or theoretical determinations. They were confirmed by the Plasma Wave Subsystem instruments on each spacecraft, which directly measured the dramatic change in plasma density that marks the transition from heliospheric plasma to interstellar plasma. The density of the plasma that the Plasma Wave Subsystem directly sampled jumped dramatically the moment each spacecraft crossed the heliopause. Before the crossing, solar wind plasma. After the crossing, the far denser interstellar medium. And in that interstellar medium, the Plasma Wave Subsystem began detecting something. To understand what that something is, you need to understand how the Plasma Wave Subsystem works. The instrument consists of a pair of electric antennas, essentially long, thin conducting rods extending outward from the body of the spacecraft that measure the electric field of plasma waves in the surrounding medium. When charged particles in a plasma are disturbed by a shock wave, by a change in the magnetic field, by a disturbance propagating outward from the sun, they oscillate. Those oscillations produce electric field variations that the antenna can detect. The frequency at which those oscillations occur is directly related to the density of the plasma. In dense plasma, the oscillations are faster at higher frequencies. In less dense plasma, the oscillations are slower at lower frequencies. By measuring the frequency of the plasma oscillations that the Plasma Wave Subsystem detects, scientists can directly calculate the electron density of the interstellar medium at the location of the spacecraft. That is the foundational measurement, and it produced one of the first genuine surprises of the interstellar mission. The electron density of the interstellar medium around Voyager 1 and Voyager 2 was significantly higher than theoretical models of the local interstellar medium had predicted. Not dramatically higher, but measurably, consistently, persistently higher than the best pre-crossing estimates had suggested. Every model of interstellar space that existed before these measurements was built from observations made from inside the heliosphere looking outward. The Plasma Wave Subsystem provided the first direct in situ measurement of the actual density of the interstellar medium surrounding our solar system, and the actual density turned out to be higher than the indirect estimates had calculated. But that density measurement, remarkable as it was, is not the detection that the title of this analysis is referring to. The detection that has scientists genuinely puzzled is something specific, that the Plasma Wave Subsystem observed continuously since Voyager 1 entered interstellar space, a persistent low-level narrowband plasma wave emission that the instrument has been detecting without interruption. Not a one-time burst, not a transient spike responding to a solar event, a continuous, steady signal in the plasma of interstellar space that researchers describe as a hum that does not appear to vary significantly with solar activity. A hum that persists even in regions of interstellar space well beyond where models predicted any significant solar influence could still be felt. A hum that scientists have proposed two different physical explanations for, and cannot yet definitively confirm which explanation is correct. The first explanation is thermal plasma oscillations. In any plasma at a given temperature, the charged particles in that plasma have thermal energy. They vibrate. Those thermal vibrations produce weak, broadband electromagnetic emission at frequencies related to the plasma density and temperature. The continuous hum detected by Voyager 1's Plasma Wave Subsystem since 2017, and now also detected by Voyager 2's instrument, could be exactly that, the natural thermal buzz of the interstellar plasma at the local density and temperature. If that explanation is correct, the hum is scientifically valuable. It provides a way to continuously monitor plasma density along the spacecraft's path without needing an external event to generate a detectable signal, but it does not require a fundamentally new understanding of interstellar space to explain it. The second explanation is what scientists call quasi-thermal noise, a more complex electromagnetic emission mechanism that would indicate the Plasma Wave Subsystem is detecting something about the structure and behavior of the interstellar plasma that existing models do not fully account for. If the hum is quasi-thermal noise rather than pure thermal oscillations, then interpreting what it is telling scientists about the properties of the interstellar medium requires revising the physical models used to describe that medium. It means the interstellar environment that Voyager 2 is traveling through right now has characteristics that were not predicted by the theoretical framework built before we had an operational spacecraft in that environment to make direct measurements. Researchers have published detailed analyses attempting to distinguish between these two explanations using the data from Voyager 1's Plasma Wave Subsystem. As of August 2026, no definitive conclusion has been reached. The measurements are consistent with both explanations at some level, and distinguishing between them at the precision required would benefit enormously from additional data that only Voyager 2's Plasma Wave Subsystem, now confirmed to have at least one more year of operational life following the Big Bang procedure, can provide. That is why August 4th, 2026 matters in this story. The Big Bang procedure that NASA's Jet Propulsion Laboratory completed 2 days ago was not just an engineering achievement. It was the decision about whether humanity's only operational instrument in interstellar space would continue returning the data that might eventually answer the question about what that hum actually is. Let's talk about what the Big Bang procedure actually was, because the engineering story is extraordinary in ways that deserve careful explanation. The fundamental problem facing both Voyager spacecraft is power. Each probe was launched with 3 radioisotope thermoelectric generators, devices that convert the heat produced by the radioactive decay of plutonium-238 into electricity. At launch in 1977, each RTG produced approximately 470 watts. Plutonium-238 has a half-life of about 87 years, which means its power output decreases at approximately 8% per year. After 49 years of operation, the RTGs on each Voyager produce roughly 40% less power than they did at launch, leaving approximately 250 to 280 watts available for the entire spacecraft. Every heater that keeps a component from freezing in the negative 459 degree Fahrenheit temperatures of interstellar space draws from that power budget. Every science instrument draws from it. Every component of the telecommunication system that allows the spacecraft to communicate with Earth draws from it. And that budget is shrinking by approximately 4 watts per year as the plutonium continues to decay. The engineers managing the Voyager mission have spent years developing and refining the power management strategy that determines which components stay on and which get turned off. The sequence of instrument shutdowns over the last several years, the Plasma Science instrument on Voyager 2 in late September 2024, the Cosmic Ray Subsystem on Voyager 1 in February 2025, the low-energy charged particles experiment on both spacecraft, was the result of that ongoing calculation. The Big Bang was different from a simple instrument shutdown. A simple instrument shutdown turns off a device and removes its power draw from the budget. The Big Bang was a simultaneous swap of multiple powered devices across the spacecraft, replacing older components, drawing more power with lower power alternatives, while maintaining the precise thermal balance required to keep every critical system from freezing in the process. The thermal constraint is what made this so difficult. Interstellar space is not empty cold. It is to temperature near absolute zero cold. The spacecraft must maintain specific minimum temperatures in specific locations, or the hydrazine propellant that keeps the antenna pointed at Earth will freeze. The propellant lines freeze. The antenna drifts. Contact is lost permanently. So the Big Bang could not simply turn off old heaters and turn on new lower power heaters in sequence. It had to turn everything off and on simultaneously because any intermediate state that left a critical thermal zone without its heat source for even a few minutes risked irreversible freezing. Think of it like diffusing a bomb by replacing 3 wires simultaneously, except the bomb is older than the iPhone by 3 decades, and your wire cutters are a radio signal that takes 17 hours to arrive. That description, from a published analysis of the procedure, captures the operational reality precisely. The command was transmitted from NASA's Deep Space Network. It took approximately 17 hours to reach Voyager 2 at the speed of light. The spacecraft executed the procedure, and then the engineers waited another 17 hours for the confirmation signal to travel back. Nearly 2 full days between sending the command and knowing whether it worked. It worked. 3 instruments preserved: the Triaxial Fluxgate Magnetometer, the Plasma Wave Subsystem, and the Cosmic Ray Subsystem. The CRS had been scheduled for shutdown before the end of 2026, now postponed by at least a year. Data still trickling home at 160 bits per second from interstellar space, roughly 500,000 times slower than a typical domestic broadband connection, but still coming, still carrying measurements of a region of space that no other instrument has ever sampled. Now let's return to what those instruments are actually measuring, because the scientific story of what Voyager 2 is currently doing in interstellar space has several dimensions that deserve examination. The magnetometer is measuring the interstellar magnetic field directly. This is a measurement that is fundamentally impossible to make from inside the heliosphere. The sun's magnetic field, carried outward by the solar wind, dominates the interior of the heliosphere and masks the interstellar field. From inside the heliosphere, astronomers can infer properties of the interstellar magnetic field, from polarization of light from distant stars, from the behavior of cosmic rays entering the heliosphere, from theoretical models constrained by multiple indirect observations. But none of those methods give you a direct measurement. The magnetometer on Voyager 2, taking readings at 13, 3 billion miles from Earth in the actual interstellar medium, is the only instrument in existence providing direct measurements of the interstellar magnetic field at this location and in this region of the galaxy. What those measurements have shown is that the interstellar magnetic field in the region surrounding our solar system is more ordered, more smoothly structured, than some pre-crossing models had predicted. The transition from the disordered, turbulent magnetic environment at the heliopause to the more structured interstellar field beyond it was measured with a precision that no other observation technique could have provided. And the implications of that structure extend to questions about how cosmic rays propagate through the galaxy, how the heliosphere interacts with the interstellar medium over long timescales, and how the local interstellar environment has shaped the conditions within our solar system over billions of years. The Plasma Wave Subsystem is doing something both simpler and more complex simultaneously. The simple version is that it is measuring the density of the interstellar plasma at Voyager 2's location by detecting the frequency of plasma oscillations. The more complex version is that it is providing a continuous record of how that density varies as the spacecraft moves through different regions of the interstellar medium, and how the plasma responds to disturbances that propagate outward from the Sun even at distances of 13 billion miles. Solar events, large coronal mass ejections, periods of intense solar wind activity, produce disturbances that propagate outward through the heliosphere and eventually reach the heliopause and interact with the interstellar medium beyond it. The Plasma Wave Subsystem on both Voyager spacecraft has detected these interstellar medium responses to solar events, providing a way to probe the structure of the region just beyond the heliopause from a vantage point, well inside the interstellar medium. And then there is the hum, the persistent narrowband plasma wave emission that does not appear to require a solar event to produce it, that persists continuously as the spacecraft travels deeper into interstellar space, and that theoretical analysis has not yet definitively placed in one of the two available physical explanatory categories. Researchers have estimated the frequency of this emission to be approximately 2 to 3 kilohertz, placing it at extremely low frequencies that cannot be detected by any antenna on Earth, frequencies at which the Earth's ionosphere is opaque, and radio waves cannot propagate from space to the surface. The only way to detect these emissions is with an instrument in space, far from Earth's ionosphere. And the only instruments currently operating in the relevant region of space are the Plasma Wave Subsystems on Voyager 1 and Voyager 2. There are 667 gigabytes of archived scientific data from the Voyager mission. Scientists in August 2026 have analytical tools that did not exist when most of those data were collected. The combination of the archived record and the new data still coming in at 160 bits per second is producing a scientific picture of the local interstellar medium that is continuously being refined and occasionally upended as new analyses reveal features that earlier processing missed. One of those features concerns how the density of the plasma in the interstellar medium has changed as Voyager 2 has traveled farther from the heliopause. The plasma density measured by the Plasma Wave Subsystem has not remained constant. It has shown a gradual increase as the spacecraft moves deeper into interstellar space along a particular direction in the sky. That gradient was not confidently predicted by pre-crossing models. Its existence means that the local interstellar medium is not uniform. It has structure, varying density, different regions with different properties, and Voyager 2 is moving through that structure in real time, providing measurements that no telescope or ground-based instrument could substitute for. There is also the question of what Voyager 2's measurements reveal about the heliosphere itself by measuring it from outside. From inside the heliosphere, scientists can study the heliosphere from the inside only. The boundary, the heliopause, can be approached from within, but the view is always interior looking outward. Voyager 2's instruments, now sampling the interstellar medium from outside, are providing the first operational measurements that constrain the shape and behavior of the heliosphere viewed from its exterior. The crossing itself was revealing. Voyager 2's crossing of the heliopause occurred at a different location in the sky from Voyager 1's crossing, and at a different distance from the Sun, roughly 119 astronomical units for Voyager 2, compared to approximately 122 astronomical units for Voyager 1. The different crossing distances at different sky locations is direct evidence that the heliosphere is not spherically symmetric. The pressure of the interstellar medium is not equal in all directions, and the heliosphere's boundary responds to those asymmetries. The Big Bang procedure on Voyager 2, confirmed successful on August 4, 2026, extended the operational lives of the 3 remaining instruments by at least 1 year. The engineering team is now planning a similar procedure for Voyager 1, which is down to just 2 instruments, the magnetometer and its own Plasma Wave Subsystem, following the shutdown of the LECP in April 2026. If the Voyager 1 Big Bang succeeds as planned, it may even enable the repowering of the LECP instrument that was shut down, providing a second chance to resume measurements that were lost when the power budget unexpectedly collapsed following a February roll maneuver. Every year of additional operation is a year of measurements from a location that no replacement mission can reach within any human planning horizon. The next spacecraft capable of reaching the interstellar medium, if funded and built and launched today, would not reach the heliopause for at least 25 years. There is no replacement for what the Voyagers are doing. The only way to extend the window of observation is to keep the hardware that is already there alive as long as physically possible. That is precisely what the engineers at JPL were doing on August 4th, 2026, when they sent the command that would become either the successful Big Bang or the end of Voyager 2's science operations. They waited 17 hours for the command to arrive. They waited another 17 hours for the confirmation to return. And when it came back, it told them that 3 instruments were still alive in the interstellar medium, still sampling the environment beyond the edge of the solar system, still listening to whatever the plasma between the stars is saying. including, still, the persistent hum at 2 to 3 kilohertz that began showing up in the Plasma Wave Subsystem data after Voyager 1 crossed the heliopause in 2012, and that Voyager 2's instrument has been confirming from its own location since 2018. The hum that either is or is not something that existing physics fully explains. The hum that requires more data to definitively characterize. The data that only the Plasma Wave Subsystem of an operational spacecraft in interstellar space can provide. The procedure that saved that instrument for at least one more year cost roughly 4 years of planning and testing, hundreds of engineers contributing over approximately 12 months of detailed preparation, and a 17-hour wait at the speed of light to learn whether any of it worked. According to the Voyager mission manager, this was a team effort, the culmination of a year of work, with almost every team member contributing. The 3 instruments preserved are not random survivors. They are the instruments most scientifically suited to what Voyager 2 is now doing, drifting through interstellar space at roughly 34,390 miles per hour, 55,370 kilometers per hour, sampling an environment no other operational spacecraft has ever reached. Voyager 2 was launched in 1977 with 10 science instruments intended to last 5 years. It is operating in interstellar space in 2026, with 3 of them still functioning. It crossed into interstellar space in 2018, 8 years ago. It is currently approximately 21.5 billion kilometers from Earth. The signal carrying its measurements home travels at the speed of light and takes approximately 20 hours to complete the journey. And when that signal arrives, it carries in its 160 bits per second, the only direct measurements from interstellar space that any civilization in the documented history of human exploration has ever obtained. Whatever the hum at 2 to 3 kilohertz is, thermal plasma oscillations, or something that requires revising our models of interstellar space, the Plasma Wave Subsystem is still measuring it. As of August 6, 2026, for at least one more year, it will keep measuring it. And the engineers who kept a 49-year-old spacecraft alive by sending an irreversible command 17 hours across the universe to make that possible are the reason the question of what that hum is has not yet gone permanently unanswered. The signal is still coming. It takes 20 hours to get home, but it is coming. And it is telling us something about the space between stars that we built no other instrument capable of hearing, until we accidentally kept one 49-year-old spacecraft running long enough to find out.